So now let's move on to step 4, making our decision. So, as we saw before, we always turn to handy dandy Tom the Toolman Taylor to help us with the tools that we need to actually make that decision. So we know that we have our chi-square test statistic already, which was 19.671. And then we need our significance level. And what do we usually have our significance level set at? 0.05. Now notice, what's different about this specific tool? Normally, whenever we're working with t-test and correlation coefficient, we have to talk about the tails. But as we'll see, chi-square analysis is just like the f-test, where we don't have to worry about the tails because our test statistic will always be positive. Thus, it's always going to be one tail, which is always going to be your right tail because it's always going to be positive. And we'll talk about that in just a few slides. So now let's turn to our third tool that we need, our degrees of freedom. So, Bobby the Bear, what's our degrees of freedom for chi-square? Degrees of freedom for chi-square is equal to r minus 1 times c minus 1. Well, what's r and c mean, Bobby? Well, r is equal to the number of rows, which is essentially the number of groups of your IV, and c is the number of columns, which is also the number of groups that you have within your DV. Thanks, Bobby the Bear. All right, so think about our example of occupation and political party affiliation. Which one's our IV? Occupation. And how many groups do we have within our IV? Well, we have teachers, salespeople, and farmers. So we have 3. And what about our DV, political party affiliation? How many groups do we have on our DV? We have Democrats, Republicans, and Independents. So we have 3 as well. So given that, let's just plug that into our degrees of freedom formula to give us degrees of freedom equal to 4. There we go. So now we have our third tool that we need, our degrees of freedom, which we found to be equal to 4. So now our last tool, critical value. This is in the back of your book on page 381 and also provided to you in titanium within your in-class exercises for chapter 17. So our last table, not that table, beer pong table, hey, but this table, critical values for the chi-square test. So let's take a look at how we read this table. So we have our chi-square test statistic, 19.671. We have our second tool of alpha equal to 0.05, and we have our degrees of freedom of equal to 4. So, like we see in our table, we have level of significance, 0.1, 0.05, and 0.01. So we know that our alpha level is set at 0.05, so we're going to look down this column. And we've calculated our degrees of freedom is equal to 4, so we're looking at this row, which gives us a critical value equal to 9.49. Pretty straightforward. So now we have all of our tools that we need in order for us to make our decision. So let's talk about the rule to actually make our decision. So here we go. Here is the rule. It is the exact same rule that we have for ANOVA. Again, notice the shape of this is very similar to our f-test, where we're looking at just the right tail of our normal distribution curve. And this is because, if you recall, the formula for chi-square test statistic, the numerator, we're always squaring our residual. So there is never a possible way that we can have a negative chi-square test statistic. And this is one of the reasons why we square the residuals, is so that we can not have a negative test statistic, which allows us really to just test one tail and really look at just one critical value. So we have here our critical value region, so we can put that as our critical value of equal to 9.49. And then we found that our chi-square test statistic was equal to 19.671. So where do you think that's going to be relative to your critical value? To the left or to the right? To the right. And that means that it's going to be obviously larger than your critical value, which we see if we look at the rule, we're going to reject the null. And at the same token, we see that our test statistic falls within the rejection region. So we're going to reject the null. We've made our decision. There we go. Woohoo! So we know that there are now significant differences between occupations on political party affiliation. So let's take a look at how we would end up stating our conclusions. So whenever we're reporting our results for chi-square test, we're always reporting your chi-square test statistic, your degrees of freedom, our p-value, if we know the p-value, which where do we get our p-value? If we do know it, from SPSS. Or if we don't know it, then we state our significance level. P is less than or equal to 0.05. So here's your template. There either was a significant difference among your IV on your DV, or there was not a significant difference among your IV on your DV. And then we're stating your chi-square test statistic immediately, followed by your degrees of freedom, and then your significance or your p-value. But then if it's significant, then we need to look at the residuals to actually find those differences and talk about those differences. So let's take a look at some SPSS output to actually make our decision. And we can actually refer back to the crosstabs table or the contingency table that we created earlier, because that's the exact same table that we did to give us our test statistic. But I just want to show you here how you would go about running the chi-square test statistic in SPSS. So you go to Analyze, and what's something different is you're going to go to Descriptive Statistics and go to Crosstabs. Once you're in Crosstabs, you select your rows to be your independent variable, and then you select your columns to be your dependent variable. You want to click on Statistics to give you your chi-square test statistics, and also your cells to also give you your expected counts and your residuals. So I encourage you to take a look at video 4 in week 10 in reference to the zombie dataset to help you walk through the steps to run chi-square analysis in SPSS. So let's take a look at the output. This is the exact same contingency table that we created by hand previously. Right? We see the 26 Democratic teachers, we see the 17.5 expected counts, and we see the residual of 8.5. And we see the entire sample of 100 people. So the first table that you're going to get, you're really technically going to get 3 tables. The first one is just going to be a case processing summary, what talks about how many people are in your sample and all that mumbo jumbo. We don't have to worry about that particular table. What you do want to worry about, and what you always want to include in your work for chi-square analysis, are these 2 tables, your crosstabs table and then your chi-square test analysis. So we see in our second table, Pearson's chi-square is equal to 19.671, which is what we calculated by hand. Well, kind of, sort of, what you saw, how we calculated that by hand, if we were to do it that way. We do have our degrees of freedom, which we did do by hand, and now we see our p-value, which is equal to 0.001. So if we compare this p-value to our alpha level, we're going to reject the null, which is the exact same decision that we made when we compared our chi-square test statistic of 19.671 to our critical value of 9.49. So those 2 decisions match up. And since we did, we're going to state our first part of our conclusion as there was a significant difference between occupations on political party affiliation. Chi-square is equal to 19.671 with 4 degrees of freedom. Our p-value is equal to 0.001. But because we found a significant difference and rejected the null, we have to look at the crosstabs table, particularly your residuals, to help you then talk about, well, where are those significant differences? Just like we did with our t-tests, we had to talk about the mean difference, or the mean increase, or the mean decrease, and then the effect size. We know with ANOVA, if we had significant differences, we had to look at Tukey's test and talk about which groups significantly differed from each other. We know that when we had to talk about significant relationships between two variables and correlation coefficient, we then had to talk about and elaborate and calculate and interpret your coefficient of determination and talking about the shared variances between the two variables. Well, when it comes to chi-square analysis, whenever we find out that there are significant differences between your groups on your independent variable, we have to look at the residuals in order for us to figure out, well, where really are those significant differences. And what I like to do is really look at what are the largest residual numbers, whether that be the most positive number or the smallest negative number. And really using the big numbers, whether how positive they are or how negative they are, to really talk about this is probably where those significant differences really lie, right? Whenever we think about your observed count, which when you look at an SPSS crosstabs, it doesn't say observed, it just says count. Remember, when it just says count, this is what we observed, we actually saw within our sample. But the bigger the residual is most likely where that significant differences lies, right? If we expected to see 17.5 Democratic teachers, but in fact we actually saw 26, that's quite a bit more Democratic teachers than what we expected. Same thing with Republican salespeople. We expected to only see about 12 people, but we actually saw almost 6 more people. We saw actually 18 people. So in this respect, your follow-up conclusion statement would be a higher proportion of teachers were Democrat, salespeople Republican, and farmers independents. There is not really going to be a particular statement that I'm looking for. Sometimes it's very clear. But the general rule of thumb when it comes to stating your follow-up conclusions for significant differences for chi-square analysis is look at the biggest residual number. You can look at the most positive number and talk about that being the higher proportion of whatever it is that you see. Make sense of it. Take a look at the data and tell a story and talk about, oh, we ended up seeing more of these people and less of these people. That's where significant differences lie. So to summarize, chi-square test is used to examine the relationship between two nominal ordinal variables. And we look at the differences between the groups within your independent variable. So while it's looking at the relationship between these two and really looking at how independent they are, remember, chi-square tests for independence, how independent are our two variables, are these two events. And we can tell that by looking at the differences between the groups on our independent variable. So the chi-square test can be a little different from what we looked at. And this is why it's a non-parametric test, because it's not necessarily a difference test, not necessarily a relationship test, but it kind of does both. And we're not really working with means, we're just talking about counts and frequencies. So again, chi-square test is a function of the extent to which observed frequencies, what do we actually see in our sample, and how much what we actually see, our observed counts, differ from our expected counts. And we will look at this within a contingency or crosstabs table. And if we end up accepting the alternative hypothesis and rejecting the null, then we have to look at the residuals for each cell to help us talk about the differences between the two variables. Again, look at the biggest positive residuals and talk about those differences within your IV and DV. All right, we're done. This is the last lecture of the semester. Woohoo!